Hello, everyone. Welcome to the Analog Electronic Technology course. From our previous lessons, we've learned that introducing negative feedback into an amplifier reduces its gain. So why do we still apply negative feedback? The key reason is that while the gain is indeed reduced, many other performance metrics of the amplifier are significantly improved. So, which specific performance aspects are enhanced? That's exactly what we'll explore in this lesson: how negative feedback affects amplifier performance. The main effects of negative feedback on amplifier performance include the following: 1. Improved gain stability. 2. Reduction of nonlinear distortion and suppression of noise within the feedback loop. 3. Effects on input and output resistance. 4. Extended bandwidth. Let's now take a closer look at each of these in detail. We already know that the closed-loop gain of a negative feedback amplifier can be expressed as shown in equation 1. In the mid-frequency range, the effect of frequency can be ignored, and we focus only on the magnitude. Therefore, equation 1 can be rewritten in terms of magnitude as equation 2. By differentiating and rearranging equation 2 with respect to A, we obtain that dAF divided by D equals 1 plus AF squared inverse. Dividing both sides of this expression by AF gives equation 3. dEF divided by AF equals 1 plus 1 over AF times D over A. Here, dAF divided by AF represents the relative change in closed-loop gain, and D divided by A represents the relative change in open-loop gain. This shows that the relative change in closed-loop gain is 1 over 1 plus AF times the relative change in open-loop gain. This indicates that the relative stability of the closed-loop gain is improved. Moreover, the larger the value of 1 plus AF, that is, the deeper the feedback, the greater the stability. However, it should be noted that the improvement in stability comes at the cost of reduced closed-loop gain. For example, if the relative variation of the open-loop gain is 10% and the feedback depth 1 plus AF is 100, then the relative variation of the closed-loop gain can be calculated to be only 0.1%. At the same time, as shown by equation 2, the closed-loop gain AF is reduced to 1/100th of the open-loop gain. This illustrates the first effect of negative feedback on amplifier performance: improved gain stability. The second effect of negative feedback on amplifier performance is its ability to reduce nonlinear distortion and suppress noise within the feedback loop. Since semiconductor devices used in amplifiers are nonlinear, they introduce nonlinear distortion. Suppose the input signal Xi is a sine wave. Without negative feedback, after passing through the basic amplifier A, the output exhibits distortion where the positive half cycle is slightly enlarged, while the negative half cycle is slightly reduced. When negative feedback is applied, and assuming the feedback network is composed of linear resistive components, the feedback signal XF will also carry the same type of distortion as the output signal, meaning the positive half cycle is slightly enlarged and the negative half cycle is slightly reduced. Now, subtracting Xi from XF yields the net input signal XID, which exhibits opposite distortion where the positive half cycle is slightly reduced, and the negative half cycle is slightly enlarged. This signal is then amplified by the basic amplifier A, and the resulting output corrects the original distortion, making the final output signal approximately a symmetrical sine wave in both the positive and negative half cycles. In other words, negative feedback reduces waveform distortion. By the same principle, negative feedback can also suppress noise within the amplifier's feedback loop. It's important to note that negative feedback can only reduce distortion or noise that originates within the feedback loop. If the distortion or noise comes from outside the loop, applying negative feedback will have no effect. The third effect of negative feedback on amplifier performance is its effect on input and output resistance, and this effect depends on the specific feedback configuration used. The effect on input resistance depends on how the feedback network is connected at the input and is independent of the sampling method. Conversely, the effect on output resistance depends on how the output signal is sampled and is independent of the input side connection. Let's now look at these effects one by one. Let's first look at the effect on input resistance. If the circuit uses series negative feedback, meaning the feedback network is connected in series with the amplifier at the input, the circuit is shown as in the diagram. Based on the definition of input resistance, input voltage divided by input current, we can derive that the closed-loop input resistance or IF equals to 1 plus AF times or I. In other words, with series negative feedback, the input resistance increases to 1 plus AF times the open-loop input resistance without feedback. This can be understood intuitively. Series negative feedback is equivalent to adding an extra resistance in series with the input path, thus increasing the overall input resistance. Similarly, if the circuit uses shunt negative feedback, it can be derived that the closed-loop input resistance or IF is equal to or I divided by 1 plus AF. This means that with shunt feedback, the input resistance is reduced to 1 over 1 plus AF times the open-loop input resistance without feedback. We can also understand this intuitively. Shunt negative feedback is equivalent to adding a resistor in parallel with the input path, which decreases the overall input resistance. It's important to note that the effect of negative feedback on input resistance is limited to components within the feedback loop. It does not affect resistances that lie outside the loop. Now let's look at the effect of negative feedback on output resistance. If the circuit applies voltage negative feedback, the feedback network samples the output voltage and connects in parallel at the amplifier's output, as shown in the diagram. To determine the output resistance, we set the input signal to 0 and disconnect the load resistor RL. Then, we apply a test voltage Vt at the output, which produces a corresponding test current It. The output resistance ROF is then given by the ratio of Vt to It. To simplify the analysis, we assume the input resistance of the feedback network is extremely high, meaning the shunting effect of the feedback network on It can be ignored. Under this condition, the closed-loop output resistance ROF is equal to RO divided by 1 plus AOF. Here, AO represents the gain of the basic amplifier when the load is open-circuited, and RO is the open-loop output resistance. From this, we can see that introducing voltage negative feedback reduces the output resistance to 1 over 1 plus AOF times the open-loop output resistance without feedback. In other words, the output resistance decreases. Using the same approach, it can be derived that with current negative feedback, the closed-loop output resistance ROF equals RO multiplied by 1 plus ASF, whereas is the gain of the basic amplifier when the load is short-circuited. From this, we conclude that introducing current negative feedback increases the amplifier's output resistance to 1 plus ASF times its open-loop value, meaning the output resistance becomes larger. Note that the effect of negative feedback on output resistance is also limited to components within the feedback loop. It does not affect resistances outside the loop. Based on the above analysis, the effects of negative feedback on an amplifier's input and output resistance can be outlined as follows. 1. The effect on input resistance depends on how the feedback network is connected at the amplifier's input. Series feedback increases the input resistance. Shunt feedback decreases the input resistance. 2. The effect on output resistance depends on the sampling method of the feedback network at the amplifier's output. Voltage feedback decreases output resistance, helping to stabilize the output voltage. Current feedback increases output resistance, helping to stabilize the output current. 3. The magnitude of these effects on input and output resistance depends on the feedback depth 1 plus AF. Generally, the deeper the feedback, the greater the effect. 4. The effect of negative feedback on input and output resistance comes at the cost of reduced gain and applies only to resistances inside the feedback loop. Resistances outside the loop remain unaffected. The fourth effect of negative feedback on amplifier performance is that it extends the bandwidth. As we know, frequency response is one of the most important characteristics of an amplifier, and bandwidth is a key technical parameter of that response. Introducing negative feedback is an effective way to expand the bandwidth. To simplify the analysis, let's assume the feedback network consists solely of resistive components. From our previous study of frequency response in Chapter 6, the high-frequency response of the basic amplifier can be expressed as shown in Equation 4, where AM is the open-loop midband gain, and FH is the open-loop upper cutoff frequency. Using the general closed-loop gain formula, we can derive the high-frequency closed-loop gain of the negative feedback amplifier. Here, AMF is the closed-loop midband gain, and FHF is the closed-loop upper cutoff frequency. It can be seen that after introducing negative feedback, the midband gain decreases to 1/1 plus AMF times the open-loop gain without feedback, while the upper cutoff frequency increases by 1 plus AMF times the open-loop cutoff frequency without feedback. Using the same method, we can derive the relationship between the closed-loop lower cutoff frequency and the open-loop lower cutoff frequency. It can be seen that the closed-loop lower cutoff frequency is only 1/1 plus AMF times the open-loop lower cutoff frequency, that is, it decreases. The bandwidth equals the difference between the upper and lower cutoff frequencies. So, we can conclude that introducing negative feedback raises the upper cutoff frequency and lowers the lower cutoff frequency, thereby widening the overall bandwidth. In summary, from the above study, we understand that introducing negative feedback into an amplifier can improve many performance parameters. It can enhance gain stability, reduce nonlinear distortion and suppress noise within the feedback loop, affect both input and output resistance, and also extend the bandwidth. All these effects are related to the feedback depth. Generally, the deeper the feedback, the greater the effect. However, it is important to understand that all these improvements come at the cost of reduced amplifier gain. That concludes our lesson on the effects of negative feedback on amplifier performance. Thanks for watching.